This is Khalandar Basha working as Assistant Professor in the Department of ECE. Today I am going to present the working principle of full wave rectifier with center tap transformer. Under this topic, we are going to discuss the full wave rectifier working principle and analysis. The course outcome is apply the PN junction characteristics for the diode applications such as switch, clippers, clampers and rectifiers. The rectifier is defined as it is a circuit that converts AC voltage of main supply into pulsating DC voltage using one or more PN junction diodes is called rectifier. Pulsating DC means the ripples imposed on DC component. The AC regularly reverse direction, while DC flows one direction only. Direct current is necessary for the operation of many devices such as laptop, computers, televisions, and certain power tools. Rectifier types. The various types of rectifiers are half-wave rectifier, full-wave rectifier with center tap transformer, full wave rectifier with bridge circuit, or simply we'll call bridge rectifier. If only one polarity of an alternating current is used to produce a pulsating direct current, the process is called half-wave rectification. When both polarities are used, producing a continuous train of pulses, the process is called a full wave rectification. A full wave rectifier requires two diodes for the construction of full wave rectifier circuit. A full wave rectifier circuit consists of three main components as follows: two diodes, center tap transformer, a resistive load. The block diagram of full wave rectifier with the center tap transformer is shown in the figure. It is consist of three sections. The first section is AC source section, followed by transformer section and rectifying and load section. So the AC source, usually it will be provided at 230 volts at 50 Hz. The voltage which we require for driving electronic gadgets will be at lower voltage. So the AC supply, which is of 230 volts, will be lowered by the transformer section. So whatever the output which is obtaining at the secondary windings of the transformer will be rectified using the rectifier circuit, and the output is collected across the load resistance. For working of full wave rectifier, the input applied for the rectification is a sinusoidal signal which is having two off cycle, positive off cycle, that is from 0 to pi, whereas from pi to 2 pi it is negative off cycle. The input signal, which is a voltage, is represented as small v is equivalent to Vm sin omega t, where omega t will takes the values from 0 to 2 pi. So the range for omega t we can write as 0 less than or equivalent to omega t less than or equivalent to 2 pi. For the analysis of full wave rectifier, we will analyze the circuit by considering positive off cycle first, followed by negative off cycle. So during positive off cycle, during a positive off cycle, the signal which you are applying for secondary windings will be appear between node A and D as well as D and B. During positive off cycle, the node A will be positive, node D will be negative on this side, and again here node D is positive on this side, node B is negative. Now the bias across D1, the D1 diode P-type material is connected to positive potential, N-type material is connected to a negative potential by means of resistance R. So the diode D1 is said to be in forward bias. In ideal case, the diode, whenever it is in forward bias, we can replace with a short circuit. We can replace with a short circuit during forward bias case. When it comes to D2 D2 diode, the D2 diode P material is connected to negative potential, whereas the N material is connected to positive potential. So the bias on the D2 resistance is reverse bias. In the ideal case, we will consider the diode D2 is in reverse bias and it will act as open circuited. So as D1 is in forward bias, the current will be flows in the upper circuit. So the current will starts from the positive terminal, that is A, and it will be flows through D1, diode D1, then it will be flows through node C, then it will take the path towards the resistance R, then it will be end at D. Whereas in reverse bias, as the diode is an open circuit, in the second loop no current will be flows. So what is the current direction we can consider here is, the current direction is it will start from node A, then diode D1, node C, load resistance R and node D. As the current is entering across the load resistance at node C and it is leaving at node D, so for resistance R on towards node C, it will leave positive potential, and towards D node, you will get negative potential. Now the voltage drop across the load resistance, we are going to be considered as output voltage V0. We are measuring the voltage at node C with respect to node D. So as the positive off cycle is flowing through the load resistance, the output we can get from 0 to pi is same as that of the input voltage. So during 0 to pi, we are going to get the current from the node A to node C, node D. As D2 is reverse bias, it is open circuited, so no current will be flows through the D2 resistance. Now during negative off cycle, the input voltage which is appearing across the secondary winding of the transformer is negative off cycle. During this negative off cycle, the node A will be negative, node D on this side it will be positive, node D on this side it will be negative, node B is positive. Now the biasing across D1, if you see, the P material of D1 diode is connected to negative potential, the N-type material is connected to positive potential through resistance R. So the bias on diode D1 is reverse bias. In ideal case, the diode D1 will act as open circuited. In the lower section, the diode D2, the P material of diode D2 is connected to positive potential. The N-type material is connected to negative potential. So the diode D2 is said to be in forward bias. In the ideal case, we can consider the diode D2 as short circuited. So as D1 is reverse bias, in ideal case, it will act as open circuited. Whereas D2 is conducting, so we can expect some amount of current is flowing in the lower section. The current will start from the positive potential in the lower section circuit, that is node B. Then it will be flows through diode D2. Then it will be reaches to node C, then resistance R, then node D, and it will end at negative potential. The current direction in this case is, the current is starting at node B. Then it will be flows through the diode D2, then reaches to node C, load resistance R and node D. Here, as the current is entering at node C and the current is leaving at node D for resistance R, so which is going to leave positive on node C and negative on node D, and we are taking the voltage across the resistance R. In this manner, C is measuring node and D is reference node. In the both the cases, positive off cycle as well as negative off cycle, across the load resistance, the current is flowing in the same direction, that is from node C to node D. As in the both the cases, the current is flowing in the same direction, the output here we can see the positive voltage, because node C is our measuring node which is at positive potential. D is reference node which is at negative potential across the resistance R. So the output across the load resistance for negative off cycle, we will get a positive voltage, that is from pi to 2 pi. So during pi to 2 pi, we will get the output voltage across the resistance R. Right. Note D2 is forward bias, D1 is reverse bias. Ideally, we know that diode D1, as it is forward bias, short circuit, whereas D2 is reverse bias, it will be open circuit. So at a glance, we can tell the full wave rectifier as a high AC voltage is applied to the primary side of the step down transformer. The obtained secondary low voltage is applied to the diode. The diode is forward bias during positive half cycle of the AC supply and reverse bias during the negative half cycle with respect to D1 diode. With respect to D2 diode, the diode will be forward bias during positive half cycle and the diode D2 is forward bias during negative half cycle. The output across the load resistance for a full wave rectifier, we can plot as shown in the figure. The input is a sinusoidal signal which is having a time period of 0 to 2 pi. From 0 to pi, diode D1 is conducting. So we are going to get the current across the D1. So from 0 to pi, we are going to get the output across the load resistance because of the conduction of D1 diode. During a negative half cycle, the diode D2 will be conducts and the output voltage will be obtained across the load resistance from pi to 2 pi. As in both the cases, the current is flowing in the same direction. So we are going to get the output voltage in the same direction. That is positive voltage for D1 diode conducting as well as D2 diode conducting. So the total output across the load resistance is the sum of the output for positive half cycle as well as negative half cycle. So we can say the output across the full wave rectifier from 0 to pi and pi to 2 pi and 3 pi 4 pi like this. The output voltage is expressed as V is equivalent to Vm sin omega t. For the output voltage, it is a periodic signal with a period of pi. So omega t is in the range from 0 to pi. So we can write the output voltage V is equivalent to Vm sin omega t, 0 less than or equivalent to omega t less than or equivalent to pi. Here, the time period of the output, if I take the T naught, the time period for the output signal, we can take as pi. So, for a full half wave rectifier, the time period is 2 pi, whereas for full wave rectifier, the time period is pi. This is one major difference. Assuming that the diode has a forward resistance of RF ohms and infinite resistance in reverse bias, that is infinite resistance for a reverse case, the current flowing through the output resistance RL, it is given as I is equivalent to Im sin omega t, where omega t is take the values from 0 to pi, that we can write 0 less than or equivalent to omega t less than or equivalent to pi. For analyzing the full wave rectifier efficiency, few parameters used for explaining the analysis of full wave rectifier. They are DC output current, DC output voltage, RMS current, root mean square current, RMS voltage, that is root mean square voltage, ripple factor, rectifier efficiency, output frequency, peak inverse voltage, peak factor, form factor, and transformer utilization factor. So the first analysis will take for average or DC output current. The average current of a periodic function is defined as the area of one cycle of the curve divided by the base. So for a full wave rectifier, the signal is confined for a period of 0 to pi. So the time period we are going to be considered here is T is equivalent to pi. The IDC expression can be related as 1 by T integral 0 to T I d omega T, where T is used as pi. During this time, the current I is equivalent to Im sin omega t. Substituting I as Im sin omega t, we can rewrite IDC expression as IDC is equivalent to 1 by t integral 0 to t id omega t will be replaced as t is equivalent to pi. So 1 by pi integral 0 to pi I we can replace as Im sin omega t, and we are integrating with respect to d omega t. Integrating 0 to pi for Im sin omega t with respect to d omega t. So Im is a constant, so that we can take outside. So the integral of sin omega t is minus cos omega t. Applying the lower limit as 0, upper limit as pi, we can write IDC is equivalent to Im by pi minus cos omega t, where omega t is taking the lower limit as 0, upper limit as pi. Substituting upper limit minus lower limit, we can rewrite as Im by pi minus cos pi minus of minus cos 0. Minus, if you take as common, you can write as minus cos pi minus cos 0. As we know, a cos pi is equivalent to minus 1 and cos 0 is 1. So we can write IDC is equivalent to Im by pi minus of minus 1 minus cos 0 is 1. Substituting this value, we will get IDC is equivalent to 2 Im by pi. As Im is the peak current, in terms of voltage, we can write as Vm divided by Rf plus Rl. In the circuit, the diode resistance we are considering as Rf and the load resistance as RL. So then IDC we can express as either 2 Im by pi, or in terms of voltage we can write as 2 Vm by pi into Rf plus Rl. The second parameter is average or DC output voltage. The VDC, it is given as the output voltage, the DC output voltage across the load resistance RL. So which is gives VDC is equivalent to IDC into RL. Where IDC, if you we can substitute as 2 Vm divided by pi into Rf plus RL into RL. If the resistance of RF as the forward resistance of the diode is very less compared to the load resistance, so we will take a constraint, that is if RF is much less than RL. Now if we substitute in VDC, we can write VDC is equivalent to 2 Vm by pi into numerator is RL. RF, as RF is much less than RL, we can write RF plus RL is approximately equivalent to RL. So by writing RL get cancelled. So which we are going to get 2 Vm by pi. This is the DC or average output voltage. The third parameter is RMS current, which is a root mean square current. The RMS current is expressed as IRMS is equivalent to square root of 1 by t integral 0 to t I square d omega t. Root mean squared. So root is present, mean means divided by the total time period, and squared current, that is I square d omega t. Substituting t is equivalent to pi, then IRMS we can rewrite as square root of 1 by pi integral 0 to pi I square d omega t. In the interval 0 to pi, the current is Im sin omega t. Substituting this, the IRMS we can rewrite as square root of 1 by pi integral 0 to pi Im sin omega t whole square into d omega t. Here the integration we are doing with respect to omega t. So Im is a constant with respect to omega t. So that we can take as constant. We can take outside of the integral. Then we can rewrite as Im square divided by pi integral 0 to pi sin square omega t we can write in terms of cos omega t. As we know, cos 2 omega t is equivalent to 1 minus 2 sin square omega t. So from this, the sin square omega t we can write as 1 minus cos 2 omega t divided by 2. Substituting sin square omega t as 1 minus cos 2 omega t divided by 2, and integrate with respect to omega t in the range 0 to pi. We can rewrite this expression as Im square root of Im square by 2 pi 0 to pi 1 minus cos 2 omega t, as 2 is a constant that we are taking outside of the integral. So here integrate 1 with respect to omega t, integrate cos 2 omega t with respect to omega t. Then we can write IRMS is equivalent to Im square by 2 pi integral of 1 is omega t minus cos 2 omega t is sin 2 omega t divided by 2. The lower limit is 0 and the upper limit is pi. Substituting the upper limit minus lower limit, we can get IRMS as Im square by 2 pi in place of omega t. Upper limit is pi and lower limit is 0. So pi minus 0 minus of sin 2 omega t. Substituting with upper limit as pi and lower limit as 0 for omega t. So then we'll get sin 2 pi minus sin 0 divided by 2. As sin 2 pi is equivalent to 0 as well as sin 0 is equivalent to 0, then IRMS is reduced to square root of Im square by 2 pi. Pi minus 0 will give us pi. So pi get cancelled. Left out is square root of Im square by 2, which Im square we can take outside of the square root. That will get as Im by root 2. As we know, Im is equivalent to Vm by Rf plus RL. IRMS in terms of voltage we can write as Vm by root 2 into Rf plus RL. The fourth parameter is RMS voltage. The RMS voltage Vrms, it is given as IRMS into RL. Substituting IRMS as Vm by root 2 into Rf plus RL into RL. As the diode resistance Rf is much less than RL, we can rewrite that with respect to the constraint. If Rf is much less than RL, then we can write Rf plus RL is approximately equivalent to RL. Substituting Rf plus RL as RL, then we will get Vrms is equivalent to Vm by root 2, because RL get cancelled. So the Vrms for a full wave rectified standard type transformer is given as Vm by root 2. The next factor is a ripple factor. It is defined as the ratio of RMS of AC component to the DC component in the output is known as a ripple factor. So the ripple factor, it is given as RMS value of AC component, that will write as IRRMS divided by DC value of the component. Either the component you can take as voltage term or current term. So DC value of component, that is given as IDC. The relation between IRMS and IDC, IRRMS is given as IRRMS is equivalent to square root of IRMS square minus IDC square. Substituting IRRMS expression in ripple factor expression, then you'll get the ripple factor is equivalent to IRMS divided by IDC whole square minus IDC by IDC whole square. IDC get cancelled, you get as minus 1. So the ripple factor expression is square root of IRMS divided by IDC whole square minus 1. So for full wave rectifier, IRMS value, whereas IDC value, substituting for getting the ripple factor, IRMS is given as Im by root 2, whereas IDC is equivalent to 2 Im by pi. By substituting these two values in the ripple factor is given as Im by 2 divided by IDC is 2 Im by pi, substituting it whole square minus 1. Here Im get cancelled. So the left out is pi divided by 2 root 2 whole square minus 1. By calculating pi by 2 root 2 whole square, you will get as 1.232 minus 1, which is gives the ripple factor as 0.482. So this specifies 48.2% of ripples are present at the output side, whereas 100 components are present is DC components. So as we know, the ripple factor, it is given as, it is IRMS divided by IDC, which is gives as 0.482, that we can write as 48.2 divided by 100, which specifies the RMS current or ripples present at the output side is 48.2, whereas DC components you can take as 100 components. Whereas for full wave rectifier, we are getting 121 ripples, whereas DC is 100, whereas for full wave rectifier, it is only 48.2. So, the rectification of full wave rectifier is more compared to half wave rectifier. For an ideal rectifier, always the ripple factor should be low. Ideally, we will take that one as 0. How much close the ripple factor towards 0 will give us more rectification of the rectifier. The next factor is rectifier efficiency. It is the ratio of DC output power to the AC input power. It signifies how efficiently the rectifier circuit converting AC power to DC power. So the rectifier efficiency is given as eta is equivalent to output power divided by input power. In terms of percentage, we are calculating, so multiply with 100. So that we can rewrite as eta is equivalent to PDC by PAC into 100, where PDC is given as we know, power is equivalent to I square R, or VM into I, V into I, or I, V square by R, any term you can take. I am taking PDC is equivalent to IDC square into RL. For a full wave rectifier, the IDC is given as 2Im by pi. Substituting it, we will get the PDC as 4Im square by pi square into RL. Whereas PAC is IRMS into RF plus RL. As the AC is flowing through diode as well as load resistance, we are including RF plus RL. And the IRMS for full wave rectifier is Im by root 2. So IRMS square, it is given as Im by root 2 whole square, which we can rewrite as Im square by 2 into RF plus RL. Substituting PAC and PDC in the rectifier efficiency, then we can write eta is equivalent to 4 Im square by pi square into RL divided by Im square by 2 into RF plus RL into 100. Here Im square get cancelled. So left out is 4 into 2, that is 8 into RL divided by pi square into RF plus RL into 100. As the diode resistance RF is much less than RL, the rectifier efficiency eta we can write as 8 by pi square into 100, which will leads to 81.2%. So this efficiency we are defining as it is equivalent to PDC by PAC, which is equivalent to 81.2 divided by 100. It specifies if you are given 100 units of AC power, 81.2 is converted into DC power, the left out is wastage power. Whereas in half wave rectifier, it is only 40.6, whereas in full wave rectifier, the rectifier efficiency is 81.2. So more amount of power is utilized here. The wastage power is very less compared to half wave rectifier. Coming to the next factor, which is output frequency. The input signal for full wave rectifier is shown on the top, which is having a time period of 2 pi. So if I take Ti as input frequency, so which is gives as 2 pi. This is input frequency. Whereas for output, the periodicity of the output, it is given as T naught. So the output, this is time period. Input time period is T is equivalent to 2 pi. Whereas for output, the time period is given as, I'll take as T naught as pi. The frequency, the input frequency Fi, it is given as 1 by Ti, which is equivalent to 1 by 2 pi. Whereas the output frequency F naught is equivalent to 1 by T naught, which is equivalent to 1 by pi. From this expression 1 and expression 2, we can write Fi is equivalent to 1 by 2 pi, where this 1 by pi we can write as f naught, so that we can write as f naught by 2, which we can rewrite as f naught is equivalent to 2 into f. So the output frequency of full wave rectifier is double of the input frequency. Whereas for half wave rectifier, the output frequency is equivalent to input frequency. The next parameter is peak inverse voltage. It is defined as the maximum reverse voltage that a diode can withstand without destroying the junction. Either can consider upper circuit or lower circuit, where the diode is conducting in the forward bias and diode not conducting in the reverse bias. So during positive half cycle, as we know, the diode is on, so it is act as forward bias, and here we are applying a voltage of Vm, maximum voltage I am considering. So the maximum voltage which will be depleted across the resistance is Vm, whereas the secondary windings we are having a voltage of Vm. Because of this voltage, the diode D2 is in reverse bias. Now if you look the circuit from the diode wherever it is reverse bias. Now when you look the circuit from here we are having a two voltages, which is Vm across resistance R, and the secondary windings having a maximum peak is equivalent to Vm. So the total peak inverse voltage is the voltage drop across the diode where the diode is reverse bias. So now if I take the nodes as X and Y, the voltage between X and Y nodes, if you see here from into the circuit, we are able to see two voltage drops. One is voltage drop across the resistance, another voltage is voltage drop across the secondary windings. So the voltage peak inverse voltage, it is given as the voltage drop across the diode D2, which is equivalent to Vm plus Vm, which will give us 2Vm. So the voltage with which diode can be withstand is more compared to half wave rectifier. That is the advantage of full wave rectifier with the center trap transformer. The next factor we can say for analyzing the full wave rectifier is peak factor. The peak factor is defined as the ratio of the maximum value of RMS value to the alternating current. So the peak factor, it is given as peak value to the RMS value. The peak value is Vm. RMS value is Vm by root 2, which is gives as Vm get cancelled, which is equivalent to root 2, where we can write as 1.414. So the peak factor for full wave rectifier is 1.414. The next factor which is used for analyzing the full wave rectifier is form factor. The form factor is defined as the ratio of RMS value to the average value of the alternating quantity. So the form factor is equivalent to RMS value by average value. So here, what is the RMS value? RMS value for full wave rectifier with the center tap transformer is Vm by root 2, whereas the average value is 2 Vm by pi. So Vm get cancelled, Vm get cancelled, which will give us as pi by 2 root 2. Pi by 2 root 2. By estimating the value, by computing the value pi by 2 root 2, we will get the form factor for full wave rectifier is 1.11. This is the major analysis of full wave rectifier. Next, the transformer utilization factor. In the design of the power supply, the rating of the transformer should be determined. This can be done with the knowledge of DC power delivered to the load and the type of the rectifying circuit. TUF, it is given as DC power delivered to the load and AC rating of the transformer secondary. Now we will see the advantage of full wave rectifier. The rectifier efficiency of full wave rectifier is double that of the half wave rectifier. The efficiency of half wave rectifier is 40.6, where the rectification efficiency of full wave rectifier is 81.2%. This means that the convert AC to DC more efficiently in full wave rectifier rather than off wave rectifier. The ripple factor in full wave rectifier is low compared to off wave rectifier. The value of a ripple factor in full wave rectifier is 0.482 or 48.2 percentage if you write in terms of percentage, while in off wave rectifier it is about to 1.21 or 121 percentage. They have low power loss because of no voltage signal is wasted in the rectification process for full wave rectifier, whereas in off wave rectifier only the positive off cycle is rectified, whereas negative off cycle is wasted. Whereas in the full wave rectifier with the standard tap transformer, positive off cycle the upper circuit is rectified, whereas for negative off cycle the lower section of the circuit is rectified. So total the entire both the cycles are used for rectification. So the power utilization is more in full wave rectifier compared to off wave rectifier. The disadvantage of full wave rectifier is with center tap transformer. The center tap rectifier or full wave rectifier is more expensive than off wave rectifier, and it's tend to occupy a lot of space. The more expensive because of two factors. One is the transformer which we are using for full wave rectifier with the center tap transformer is a center tap transformer which is costlier than normal transformer, as well as it will occupy more space. The second difference between those two rectifiers is off wave rectifier requires only one diode, whereas full wave rectifier with the center tap transformer requires two diodes. So the various factors which we are discussed for analyzing the full wave rectifier are DC current or average current, which is 2 Im by pi, whereas DC voltage it is given as 2 Vm by pi into Rf plus RL. The RMS current is Im by root 2. Ripple factor is 40.6, whereas efficiency is 81.2. These are the major factors which we are going to be considered for evaluating the rectifier efficiency. Right. With this, I'll conclude the principle of construction and principle of operation of full wave rectifier with a center tap transformer. The performance of the full wave rectifier we are analyzed with a few parameters like DC or average current, DC or average voltage, RMS current, RMS voltage, ripple factor, rectifier efficiency by evaluating PDC as well as PAC, form factor, peak factor, output frequency, peak inverse voltage, and transformer utilization factor. Thank you all.
Like, share and subscribe. Hit the bell icon for more updates.